let's have a short review from the previous session. We talked about utility maximization, expenditure minimization. Specifically, let's talk about how to maximize different types of utility function. Basically, we have 5 types of utility function, which is very common, and we may have in any kind of problem set related to utility maximization. But they have different way of maximizing utility. So the first one, if we have a Cobb-Douglas or CS type of utility function, for example, if we have a utility function which is u x1, x2 is equal to x1 to the power of alpha, x2 to the power of 1 minus alpha, and also if we have a utility function, for example, u x1, x2, which is equal to, for example, a x1 to the power of rho plus b x2 to the power of rho whole to the power of 1 over rho. So the first type of utility function, which is like Cobb-Douglas and CS utility function, so we have like the same way of maximizing utility for these 2 different utility function. Why the same method? Because these 2 utility function, both of them can be 2-wise differentiable. If you remember the last class, we said if the utility function is 2-wise differentiable, so we can use the same method, and that's Lagrangian method. So the method that we use for the Cobb-Douglas and CS utility function is to use the Lagrangian. To use the Lagrangian method. And when we use the Lagrangian method, there's 2 steps. Step 1, to set up optimality condition. To set up the optimality condition. What's the optimality condition? The optimality condition is that the marginal utility of x1 or 1 here divided by the marginal utility of 2 should be equal to the ratio of prices, P1 over P2. And we know that the marginal utility of x1 divided by the marginal utility of x2 is equal to the marginal rate of substitution. The marginal rate of substitution. And also for the ratio of prices, we have another terminology which is called economic rate of substitution, ERS. So the first step is to set up optimality condition, which is the marginal rate of substitution is equal to economic rate of substitution. When we have this condition, so we can find out one good in terms of another good. For example, marginal utility of 1, it means here we have x1. The marginal utility of x2, here we have x2. So either we find out x2 in terms of x1 or the other way around, like x1 in terms of x2, or x2 as a function of x1, or x1 as a function of x2. Then the second step is to have our budget constraint. So like in our budget constraint, we have P1 x1 plus P2 x2 is equal to M. When we found x2 in terms of x1 or x1 in terms of x2 from this optimality condition, then we can substitute that one to here. For example, in terms of instead of x2, we can write x2 here as a function or some function of x1. Then at this budget constraint, we will only have either x1 or x2. Either x1 or x2. So when we substitute x2, a function of x1 instead of x2 here, then we will only have x1, p1, p2, and m. Then simply we can find out x1 as a sum function of p and m. So when we found x1 as a function of p and m, so that x1 is the utility maximization bundle. Is the utility maximization bundle. So then, how we can find out x2? So because we found x2 here as in terms of x1, and we substitute to the budget constraint to find out the x1. So the next step is to substitute this x1 optimal bundle instead of this function here. So because now we have x1 as a function of p and m, so we just substitute the value as a p and m to this x1, then we can find out the x2 optimal bundle as a sum function of p and m. As we already maximized the utility for this Cobb-Douglas and for the Cobb-Douglas example last week. So we can do the similar things for the CS utility function. So it's just, we need to follow this step. First, we need to use the Lagrangian, which is the common method for these two types of utility function. Then we have two steps. The first step is to set up the optimality condition, which is marginal rate of substitution is equal to economic rate of substitution. And the second step is to set up our budget constraint and find out x1 or x2 in terms of another variable or another goods here and substitute to budget constraint to find out one optimal bundle, and then again substitute that one to this condition to find out another bundle. So just two steps. So this is the common steps for finding utility maximizing bundle for CS utility function and Cobb-Douglas. So the next one, utility maximization for the perfect substitute utility function. So if we have a utility function ux1, x2 as a, for example, ax1 plus bx2 plus bx2, what method we can use for this type of utility function? So as we know, from the utility function, we can only say that this utility function is differentiable, but with degree of 1. So we can find out the first order condition, but not the second order condition. So in order to use the Lagrangian, we need to know the second order condition, or the function should be twice differentiable. If we use that method here, what will happen? So for example, if we use the Lagrangian method here, then this utility function for Lagrangian of x1, x2, and Lagrangian, it will be equal to like this u x1, x2, or just simply let's write down the value, which is ax1 plus bx2 m minus p1x1 minus p2x2. Let's do this way. So if we set up the Lagrangian for this function, which is just, we can only find out the first order condition, this is what will happen. For example, if we find out the first order condition for x1, then we will have only a here, only a, minus, from here, we will have lambda p1. And also, the first order condition for the x2, we will have b minus lambda p2. So this is 1, this is 2. And the third one, the Lagrangian in terms of this Lagrangian multiplier, it will remain that one, m minus p1x1 minus p2x2. So this is equal to 0, this is also equal to 0, this is also equal to 0. So the third one will become equal to p1 x1 plus p2 x2 equal to m, just our budget constraint. But now, as you see, the first order condition in terms of x1, we don't have any x1, x2 here. We only have A. For the x2, we only have B. So if we divide 1 over 2, so it will be equal to A divided by B. And if we move lambda P1, lambda P2 over there to the right side, then this lambda will cancel out with this lambda. We will have P1 over P2. P1 over P2. So then A over B is our marginal rate of substitution. And P1 over P2, as we know, is equal to economic rate of substitution. As you remember, in case of Cobb-Douglas and CS utility function, we said that when we find out the marginal rate of substitution and make it equal to economic rate of substitution, then we need to find out x1 as a some function of like x2, or x2 as a some function of x1. But can we do that here? Because we don't have any x1 and x2 here. We only have A over B, P1 over P2. So that's why using Lagrangian method for this perfect substitute utility function will not work. So what is the substitute way, or what we can do in order to find out the utility maximization for this type of utility function? Again, we have 2 steps. And what are those steps? Step 1. The step 1 is to find out the marginal utility per dollar of x1 and the marginal utility per dollar of x2. So if we divide the marginal utility to price, it's called the marginal utility per dollar or per amount of money or per currency. It can be anything. It can be won, it can be like dollar, it can be like any other country currency. Or marginal utility per dollar of x2. Then this is the first step. The second step is to compare this marginal utility per dollar of x1 with marginal utility per dollar of x2. It's to compare that one. So here, if the marginal utility per dollar of x1 is greater than the marginal utility per dollar of x2, so we only consume x1. We only consume x1. And if the marginal utility per dollar of x1 is less than the marginal utility per dollar of x2, then we only consume x2. So in terms of perfect substitute utility maximization, we maximize our utility by consuming that good that provide higher marginal utility per dollar. If x1 provide higher marginal utility per dollar, this is P2. If x1 provide higher marginal utility per dollar, so we consume only x1. If x2 provide higher marginal utility per dollar, we only consume x2. So in this case, our x1 as a function of P and M will be equal to M divided by P1. And in this case, our x2 as a function of P and M will be equal to M divided by P2. M divided by P2. But the third condition is, so this is step 2. The third one, if the marginal utility per dollar of x1 is equal to the marginal utility per dollar of x2, So how we can maximize our utility now? If they provide, for example, equal marginal utility per dollar.
Hence, A and the B which is higher.
They're the same. Suppose they are the same.
A and the B are same.
Yeah.
Difference.
Suppose we have this kind of utility function, U, as a function of x1, x2 is equal to x1 plus x2, and our budget constraint is equal to 2x1 plus 2x2 is equal to, for example, something 100. So now here, the marginal utility of x1 is equal to 1. The price is equal to 2. The marginal utility of x2 is equal to 1. The price is equal to 2.
It is indifferent.
So in this case, we can consume any combination. Any combination. By any combination means that we can allocate our income, which is M, which is that 100. Which is that 100. We can allocate this 100 as an income to buy X1 and X2 in any condition that we should not consume more than $100. So in terms of utility maximization for perfect substitutes, so we have these three conditions. The first one, the second, and the third. It depends on where we are. So as I said again, so we cannot use Lagrangian method here. Just we only find out the marginal utility per dollar of two goods and compare the marginal utility per dollar of goods together. We maximize our utility in the case if one good provide higher marginal utility than another one. If they provide similar marginal utility, we can consume any combination and maximize our utility in the case that we should not consume more than our income level. But the third one, okay, we already made a question for that. So the third one is utility maximization for perfect complement. So if we have a utility function u x1, x2 as a mean function, mean of ax1, bx2. ax1, bx2. So this function is not differentiable at all. Because first of all, if we have this kind of utility function, we have a kinked indifference curve. We have a kinked or L-shaped indifference curve. So maybe, for example, this is U1 and this is U2, and this is the 45 degree. So in this case, which is not differentiable, so what we can do, again, we have two steps. Step one is to equalize ax1 with bx2, because we are going to maximize our utility with the mean level. So, for example, let's suppose that x1 is your car, and x2 is the number of tires that you use for your car. So the tire and also car is complement. You cannot use, for example, car without tire. And sometimes maybe we can use tire with other purposes, but let's assume there's no other purpose for that. So we cannot use tire without car. So they are perfect complement. So in this case, we can set up the first step, which is ax equal to bx2. x1 is equal to bx2. Again, the second step is our budget constraint, which p1 x1 plus p2 x2 is equal to m. So it's easy. From the first step, for example, we have ax1 is equal to bx2, just find out the x1 in terms of x2, some function of like x2. So then it will be equal to b divided by a multiplied by x2. b divided by a multiplied by x2. So now, instead of x1 to the budget constraint, plug the value in terms of x2. So we will have p1 multiplied by b over a x2 plus p x2 is equal to m. So now we only have x2, p1, p2, and m. So it's very easy to find out x2 in terms of p1 and p2 and m. So then we can find out x2 star as a subfunction of p1, p2, and m. Because we only have p1, p2, and m. So now let's do that. We will have p1 b over a x2 plus p2 x2 is equal to m. So p1 b over a plus p2 x2 is equal to m. So finally x2 can be equal to m divided by p1 b over a plus p2. So this is the value of x2. So when we find out the value of x2 here, so then plug the value of x2 instead of this x2 here, so then we will find out the x1 x star. So now by using these 3 steps, so we can maximize the utility function when we have a perfect complement. And the last case, if we have a quasi-linear utility function. If we have a quasi-linear utility function, which we can say, yeah, utility maximization problem or process. So if we have a quasi-linear utility function, for example, we have a utility function u x1 x2 is equal to ln of x1 plus, for example, bx2. So we can say this types of utility function is a kind of combination of, for example, Cobb-Douglas and perfect substitute. Why I say that? Because here, ln of x1, it can be twice differentiable. But x2 can be just differentiable for one time. So it cannot fit to the Cobb-Douglas and CES utility function, because of the case of Cobb-Douglas and CES utility function, both x1 and x2 were twice differentiable. But the case of perfect substitute, both of them were one-wise differentiable. But here, in case of non-linear, it's twice differentiable, but in case of linear, it's just one-wise differentiable. So how we can maximize this one? Mm-hmm. A kind of, we can also use Lagrangian here. We can use Lagrangian here, but our steps has become a little bit shorter than what we use for CES and Cobb-Douglas utility function. So again, when we use Lagrangian, we should follow that step, which the first step is to set up the optimality condition. And that optimality condition is equal to marginal rate of substitution is equal to economic rate of substitution. So here, marginal rate of substitution is equal to marginal utility of x1 divided by the marginal utility of x2. And if we find out the marginal utility of x1 from this function, so the marginal utility of x1 will be equal to 1 over x, because the derivative of ln of x is equal to 1 over x. But the marginal utility of x2 is equal to just b, just equal to b. So then the marginal utility of x1 divided by marginal utility of x2 is equal to 1 over x divided by b. So it should be equal to p1 over P2. But here we have one difference than what we had in CES and Cobb-Douglas utility function. In CES and Cobb-Douglas utility function, when we set up the optimality condition, here we had both x1 and x2. We had both x1 and x2. But here we only have x1. So there is no x2 to find out x1 in terms of x2 or x2 in terms of x1. We only have one, x1, or if this is nonlinear for the case of x2, we may have only x2. So it's easy. So in order to find out x1, so then, for example, p1 b multiplied by p1 is equal to 1 over x1 multiplied by p2 divided by 1 over x1 is equal to b p1 x1 equal to p2, and then our x1 is equal to p2 divided by b p1. This is the optimal level of x1. This is the optimal level of x1. So the optimal level of x1, which is nonlinear here, it's only a function of prices. There is no income here. So then we can write down that x1 star is equal to just some function of p1 and p2. There is no price. So in the case of quasi-linear utility function, our optimal bundle for nonlinear good is just a function of prices. It's just a function of prices, which is, you see that we have P1, P2, and there is no income. So the optimal level for the x1, which is nonlinear, is just a function of prices, a function of P1 and P2. So with the first step, we're just doing the first step, we found the optimal level of one good, which is this one. Optimal of x1. We found out the optimal level of x1. But when we had like CS utility function or Cobb-Douglas utility function, we couldn't find out with just only the first step, one of them. But here it's possible because we only have one of variable. So it's easy to find out. And the second step, again, to set up our budget constraint. And the budget constraint, which we have P1 x1 plus P2 x2 is equal to m. So now substitute the value of x1, which is this one. So then P1 multiplied by P2 divided by B P1 plus P2 x2 is equal to m. So then this P1 with this P1 will cancel out. So we only left with P2 divided by B plus P2 x2 is equal to m. Then we can move that P2 over B to that side of our function. So it will be equal to P2 x2 equal to m minus P2 divided by B. Can divide both sides with P2. Then m divided by P2 m divided by P2 minus P2, not P2, divided by P2 multiplied by B. So then what will happen? This P2 with this P2 will cancel out. So we'll only have x2 as a m divided by P2 minus 1 over B. So this is the optimal level of x2. So here x2 is only a function of its own price and income. It's not a function of the price of x1. You see, in x2, we only have m and p2. We do not have any p1. So finally, we can conclude that when we have a quasi-linear utility function, our optimal level for nonlinear good is only a function of prices. But our optimal level for linear good is a function of income and its own price, not the price of other good. So this is the utility maximization process for the quasi-linear utility function. Any question? So if we have, for example, ux1, x2 as a 2x1 plus, for example, this is 3. But here, it's non-linear for x2, but linear for x1. Just in different case, the other way around. So now, how we can maximize this utility function? Can you do it?